Over the next few videos, we're going to be taking a bit of a foray into modern physics. And first off, just to start with, what do I mean by modern physics? What we found is that at the end of the 19th century, we were at a point in physics where we thought we had a pretty good handle on things. We had classical mechanics, which was very successful, and a very well developed theory of electricity and magnetism due to James Clerk Maxwell and all the prior contributors. It turned out, though, that there were a couple of small glitches in the, which is a couple of experiments that were problematic. And it turns out that to resolve those problems, we're going to actually pretty much have to jack the entire house of physics off of its foundation, pour a whole new basement, and set the house back down on a better foundation. This process took place in the early 20th century, which we view now as the era of modernity for physics. So pretty much when we talk about modern physics, we mean anything starting in the early 20th century. We're talking like the 19-teens here, and later we're having to tackle physics from a radically different perspective. So in that sense, it's modern, even though at this point modern physics is over 100 years old. So I think it'll be helpful as we go on in the next few videos to just have a bit of a working example in the back of our mind. And so to this end, I'm going to bring in what's possibly an unpleasant memory for some of you, but that will be a trip to the dentist office. Now this thing that I'm drawing right here is an X-ray tube, and I am going to way oversimplify how you build one of these things, but suffice it to say, you have a filament here, and you run a low current through the filament, getting the filament hot, and if it gets hot enough, some electrons will feel like jumping off the filament. This is all part of an assembly known as the cathode of the X-ray tube. Then up here will be a bit of an assembly known as the anode of it. So this is part of the cathode assembly. Then here is the anode. A block of metal with a very strategic angle cut into it. And then the idea is that you maintain, between the anode and the cathode, you maintain a potential difference of tens of thousands of volts. So we'll just say equals very large. And these electrons that get boiled off of the filament here, very large, there we go. Electrons that get boiled off the filament, so there's an electron, will get accelerated very rapidly here and collide with the anode. And in the process, X-rays, which are particles of light, will get emitted. And the angle is very carefully chosen here so that the X-rays will go out like this. Then the X-rays will go along, and pardon me here, if you've been watching enough of my videos, you already know how terrible of an artist I am. So I am just going to say, these are teeth. You know they're teeth because I said they're teeth. And then you stick in between the teeth a bite wing sensor, like so. You bite down on this, and then the actual business part of it is this bit right here. there is a sensor here. And the sensor is divided into a whole bunch of pixels. And what happens is when they take the exposure, X-rays get sent out of the tube through your teeth, and the ones that make it to the sensor get recorded, and you end up with an image that looks something like this. So here, the way these get read might seem a little weird. Wherever you see like a bright white area, this is actually a shadow. This means that not very many X-rays struck the sensor there. And anywhere where it's dark, like where the piece of plastic is that the patient was biting down on, this is actually where a lot of photons hit the sensor. So this is actually a bright spot. So why is the bright spot shown dark and the dark spot shown bright in these images? This has to do with older technology using photographic film. In photographic film, most photographic films wound up making what was called a negative. And then when you developed it, you would then make the positive. So in photographic film negative, dark spots appear white and white spots appear dark, but when you would make a print off of it, it would be the other way around. Well, dentists don't really need to look at a print of it. They can just look at the negative, and so they got used to just reading it backwards. Same with any other kind of X-ray that you've ever taken a look at. The dark spots are where there's a lot of X-rays hitting the sensor, and the bright spot is where there's not many X-rays hitting the sensor. And for historic reasons, they just continue to encode it like that, rather than where they reverse the black and the white from how you think you should encode the image, or at least how I would think you would. So we can take a look at this and we can pick out some things here. First off, as we can look at this, we can see that the patient has a filling here. And so what's happening is the filling is casting a shadow. The metal of the filling apparently does a pretty good job of blocking the X-rays. And so not many X-rays wind up landing on the sensor. Same here. Here, the patient has two different kinds of crowns here. This crown here is a porcelain crown sitting on a thin layer of gold. Now, although gold is very thin, it actually does a really good job of blocking X-rays from hitting the sensor. And so we wind up seeing an X-ray shadow here. Whereas the porcelain that makes the tooth look like a tooth is more transparent to the in the X-ray. And so it casts less of a shadow, thus looking darker. Yeah, I know that it's backwards. And then you can go and take a look in here, and you can see some of the structures of the tissues inside the teeth. And again, since I am not a dentist or a doctor, I'm not going to get into the nuts and bolts of what all this stuff is. But we can look over here, and we can see that we've got a different kind of crown material here. In these, the entire crown is made out of zirconium, and so you wind up getting, which also does a good job of absorbing X-rays, and so you can see a different kind of image there. So as we go along here, the things that we can get out of this. First off, for every electron that hits the anode, we wind up ejecting an X-ray, just one. And so if we think back to where we were talking about treating light as a particle versus treating it as a wave, here the particle properties of the X-ray are of the light are very much dominating, each individual X-ray photon is very energetic, and then these individual photons will interact, in this case, with some part of the tooth, and will either, if they interact, they'll get absorbed or scattered or whatever, but won't make it to the sensor. Or if they don't interact, then it passes through, and they do. So general rule of thumb is the less dense the tissue, the darker the region in the photographic negative of the X-ray. So for instance here, the tissue, for instance here, the tissue is denser, and so you see a whiter spot here. Here the tissue is less dense and you see a darker spot. And again, remember, when we see dark, this actually means that more photons hit the sensor, but they always encode light and dark in these images backwards. However, we can see that a very thin layer of, this isn't 100% true, what atom it is has a thing or two to say about. So for instance here, this is actually a very thin layer of gold, and it does a really good job of blocking X-rays from going to the sensor. So it's not 100% to say that it's purely the density of the material. It's both the density of the material and what kind of material it is. All right, so we'll just keep that in the back of our minds as we go along and think about what else we can say about these photons. About these photons of light. So what we saw before is that even though here we can very reasonably talk about each individual photon flying out, it's still the case that the wave properties of light will dictate the probability of where you will detect a photon. So just like when we were looking at more, invisible light where the wave property dominates more, and we saw double slit diffraction, stuff like that, there is a similar thing that we end up seeing in the X-ray. But the thing is we need our slits, if you will, to be spaced much closer together because the wavelength of X-rays is much shorter. And it turns out that the phenomenon that'll show this up is something called Bragg diffraction. So it turns out that if I have some sort of a crystal or any nice well-behaved molecule for that matter, but it's probably easiest to think of some sort of a crystal. The atoms in the crystal will be able to arrange themselves, can usually be organized nicely in planes. So these are different diffraction planes of our crystal. This might be, say, a crystal of nickel or something like that. So again, what you can have here is you can have as always, we measure angles with respect to the normal. So let me just go ahead and erect a normal, like so. Remember, normal is just a line that's perpendicular to the surface. So these are different layers of atoms in my crystal. Oops. And we can go ahead and send some X-rays in. So let's say I have some X-rays coming in at some angle theta. The law of reflection does indeed apply, but we're only going to reflect at particular angles because the light will also want to transmit through. So what's going to dictate whether we reflect or not? And that will be if I hit an atom on a different plane. So this X-ray came in, this photon came in, bounced off of this atom. This one bounces off of this atom. If that's the case, the wave properties will interfere. And what's going to matter here is the extra distance traveled. So this extra distance traveled here is going to be this bit plus this bit. Very much like when we were thinking about thin film interference. So each of these is going to be d, our crystal spacing, times the cosine of theta. So this extra distance traveled equals 2d cosine theta. Now it turns out that if this extra distance traveled is equal to some integer number of wavelengths, then if I had a crest coming in here, I will have a crest meeting a crest. I'll have constructive interference, just like when we were thinking about thin film interference. The difference here is that with thin film interference, we're looking straight up and down. Now we actually have to take the angles into account. So that's what differs here. So anyway, what we get is that we will see at very specific scattering angles, we will see peaks of X-ray whenever this extra distance traveled, 2d cosine theta. Now I'm going to use an m here, and just like when we were doing thin film interference and the like, this is just counting the number of possible bright X-ray peaks that we'll see whenever this equals m lambda for m equals 1, 2, 3, and so forth. And X-ray crystallographers can use this to figure out the arrangement of atoms in a material. Because, for instance, although we have these planes here, there are other planes that you will have. So, for instance, I can draw a collection of planes that go like this, and Bragg diffraction will work along that collection of planes as well. That will have a different spacing. And so when you take a complete look at the intensity of scattered X-ray light against scattering angle, you can pick out different families of peaks. And from that, you can reconstruct how the atoms had to be arranged to create all of the different crystal planes that particular crystal had. You can also even use this, say, for instance, Rosalind Franklin used this technique to map out the double helix structure of the DNA molecule. So just to give a bit of an example of this, let's say that we have some sort of crystal, and I'm not going to redraw all the molecules. I'm just going to say the Bragg planes are separated by 0.11 nanometers, which is a typical kind of size for an atom. Atoms are about roughly 1/10 of a nanometer across, so this is a typical spacing. And let's say that we had photons that were X-rays that were 12 keV. That's usually at this point you just specify the energy of the photon. Let's figure out what the first two scattering angles we could have where our sensor over here would see reflected light, it would see a peak of reflected light. So for that, we can go ahead and plug into our Bragg relation, 2d cosine theta equals m lambda. Now, we've already seen from prior video that the energy of a photon is equal to hf. And if we remember, frequency times wavelength equals speed of light. So it's often convenient to write this just as hc over lambda. So let's go ahead and put that in. So we'll say that 2d cosine theta m equals, so this will give me lambda is equal to hc over E. So we'll put that in. So this will be mhc over E. Rearranging, cosine theta m equals mhc over E. 2de, take the arc cosine of both sides. Theta m equals the arc cosine of mhc over 2de. So when you're doing this kind of a problem, something that's really handy to remember is, since this quantity h times c shows up all the time, and you're very often working in units of eV for energy and nanometers for wavelength, or interatomic spacings, it's actually really handy to remember that h times c is equal to 1,240 eV nanometers. With that, we can go ahead and substitute in for m equals 1 and m equals 2. So for m equals 1, theta 1 here will be the arc cosine of 1 times 1,240 eV nanometers over 2 times our spacing of 0.11 nanometers times our energy. We said the x-rays were 12 keV, so it's 12,000 eV. So if we check, it's always really important whenever you're taking an inverse trig function that all the units cancel, and they do, because I don't know what the arc cosine of a unit would be, so you always have to end up with a dimensionless number. When you do this, you end up getting a scattering angle of 62 degrees. And then for m equals 2, we do exactly the same thing, except we go ahead and put in 2 for m instead of 1. And we get that the other scattering angle is going to be 20 degrees. And it turns out those will be the only two, because if you try sticking in 3, you'll be taking the arc cosine of a number bigger than 1, and then you're kind of in trouble. Okay. So with that, let's go ahead and visit another problem. So remember I was saying that as we transition into the era of modernity for physics, there were a couple of problems with classical physics. One of them, which will be coming up on shortly, is the photoelectric effect. But I'd like to start with black body radiation. So just as a reminder from thermodynamics, black body radiation is the light that something emits just because it's hot. Now, before the development of modern physics, if you used classical mechanics and the theory of electricity and magnetism to calculate the spectrum of this, what you got was if I plot the intensity as a function of wavelength, at long wavelengths, everything was well behaved. But as we got to shorter and shorter wavelengths, the intensity actually just plain headed up to infinity. This actually gets called the ultraviolet catastrophe in the history of physics. The actual experimental result did actually match the classical behavior at longer wavelengths, but at shorter wavelengths it tapered down to 0. So it peaks up, and then this part here matches the classical. But then as we get to shorter wavelengths, we curve down and actually head down towards 0. And when we're talking about Wien's displacement law, exactly where this peak is differs. The hotter you are, the shorter the wavelength the peak is at. But we're just interested in the shape here. Well, this sort of thing had crept up in physics before, where you do a calculation didn't match with experiment, or in this case only partially matched experiment. And usually what's at the source of this is that the actual math of doing the calculations gets extremely difficult. And so part of the art of doing the theoretical calculations, especially over a century ago when it all had to be done by hand, was using your physics intuition to figure out what parts of the calculation you could neglect, on what you call making approximations. And so when you look at something like the ultraviolet catastrophe, people would look at that and say, oh, it looks, so this is just a case where probably too many approximations got made, the calculation wasn't done fussy enough, and then you get this garbage result as wavelengths get ever shorter. So for over a decade, some of the brightest theoretical minds in physics did more and more careful calculations, neglecting less and less. And although there would be slight changes in the shape of the curve, the overall issue that it would just keep heading off, that the intensity just head off to infinity as the wavelength kept getting shorter and shorter, that never went away, try as you might. And eventually the realization was just plain that there was some sort of flaw in our understanding of classical physics. So this is the fix. And we'll be going through, over the next few videos, we'll be refining the fix somewhat. But this fix is due to Max Planck. And we know that Planck and his colleagues were not happy about the nature of the fix that they did. And we know this because, bizarrely, it's because Planck had horrible handwriting. Because he had horrible handwriting, whenever he communicated with his colleagues, he typed everything up, and using some stuff called carbon paper, he kept a copy of everything that he typed so he could remember what it was he sent to his correspondence. So we actually have both sides of all the correspondence that Max Planck ever had with his colleagues. And as the beginnings of quantum theory are getting developed here, phrases like last desperate attempt to save physics are showing up in the correspondence. They're not happy about it, but they're realizing they have to take some really radical approach. So here's Planck's fix. Remember, the general idea of how you make a light wave is you take a pile of charge and you shake it up and down. So if you take a pile of charge, shake it up and down, you emit a light wave. What Planck did to fix the problem was he said that the allowed energies of the charge oscillating up and down, what he called resonators, the allowed energies of the resonators are quantized. And what quantized means is that they come in discrete amounts. So the total mechanical energy of this charge shaking up and down can't be just any arbitrary value, says Planck and colleagues, but it has to be some multiple of a specific value. The other thing that he has to do is he has to say that light gets emitted in discrete bundles. Which we call photons. So, there are allowed resonator energies, says Planck, will be NHF, where F is the frequency of oscillation and N is the principal quantum number. And in this case, we'll just say the quantum number. So N is allowed to be 1, 2, 3, etc. I'm glossing around 0 because it'll turn out that later we'll have to patch this up. So I'll write 0 in gray here. We're going to have to patch this up and add a half to all of our n's. This won't actually change any of the results that he did, though. So we'll stick with just this for now. And as we've already introduced, the energy of our photon energy is HF, and where F is the frequency of the light associated with the photon, and H is Planck's constant, 6.626 times 10 to the negative 34 joule seconds. Okay, so what does this do for us? It tapers down the ultraviolet so that we get to this behavior here. Because with the ultraviolet, wavelengths get short, which means frequencies get high. So what this means is that for low frequencies, our allowed energies are spaced very closely. For high energies, high frequencies, the spacing of our allowed energies is greater. And so it's just plain harder to get, so it's harder for us to change one of these frequencies to get up into a higher state. So the idea here, Planck says, is it's easy for our electrons to change allowed energies here. And because the spacing is bigger here, it's harder to change levels harder to change levels in the high frequency case. And so because it's harder to change levels, that winds up making it harder and harder and harder to get an electron that will be shaking the way you need it to emit light at these ever shorter wavelengths, and that puts the damper back down. Now, it turns out this works beautifully. It's not just like it works roughly, it's got basically perfect agreement with the experimental data. Now, the thing is that Planck's looking at it, he's got a bit of an idea of how to cut it off, but nobody has any idea why it should work this way. So this is why Planck and his colleagues were feeling unhappy about this fix. The fix itself is unmotivated. And another thing that makes everybody feel a little weird is that this applies to any oscillator. So not just the electrons oscillating up and down, but even literally, if we think back to doing, labs in mechanics, if you hang a mass on a spring, it turns out that this can't just have any old energy. It has to have only certain specific quantized energies. And so I think it's worth spending a moment revisiting this to get some idea of, is this a big deal or not, and how to interpret this. Because remember, one of the key things is whenever you introduce a new model, in this case quantum mechanics, you have to show how in some limit or other you recover classical physics where it works. So classical physics clearly didn't work here. Planck's new model fixes that, but we have to make sure that we don't break things like masses on springs. So this end, let's actually go ahead and give this some numbers. So for like a typical lab setup here, we might have 50 grams of mass hanging on something like a 10 Newton per meter spring. And let's go ahead and say that it is oscillating with an amplitude of 2 centimeters. So a nice typical lab setup here. For that, let's go ahead and calculate what quantum number we're in and see how much energy there is, what the energy difference is between levels, and see if any of this matters. So first, let's figure out the frequency that this is oscillating at. So we remember that for a mass on a spring, it will oscillate at 1 over 2 pi times the square root of k over m. So let's just go ahead and compute this. So 10 newtons per meter, newtons per meter over 0.05 kilograms. This works out to be 2.25 hertz. It's not exact, but we'll see. We don't need to get too stressed out about doing this precisely once we see what the punchline is. All right. So our total mechanical energy is 1/2 the spring constant times the square of the amplitude. And, says Planck, this has to be equal to some principal quantum number n times hf. So we can solve for our quantum number. It will be Ka squared over 2hf. All right, so this is 10 newtons per meter. Our amplitude is 0.02 meters squared over 2, 6.626 times 10 to the negative 34 joule seconds times our 2.25 hertz. All right. I am not going to write down every digit of this quantum number because my calculator can't display it. It's going to be 1.34 times 10 to the 30. So this is a very high quantum number indeed. And what is our spacing of our energy levels? Well, that'll be just HF, which is 6.626 times 10 to the negative 34 joule seconds times our 2.25 hertz. Well, it turns out that our energy spacing winds up being 1.49 times 10 to the negative 33 joules. This is really small compared to 1/2 Ka squared here, which that's, let's see, what, 0.04 times, .004. This is on the order of a few hundredths of a joule. And this turns out to be 10 to the negative 33 joules. So although you can't have any old energy level, the energy levels are spaced so finely that there is no instrumentation out there at all that can detect that our mass on a spring can't have any old energy level, but it can only have energy levels that are multiples of 1.49 times 10 to the negative 33 joules. And then when you're up in the fraction of a joule range for a setup like this, you find that it's like, okay, that's basically looks continuous. So here the correspondence principle is satisfied. The continuous behavior that we see at the macroscopic level, it isn't really continuous, but it's so super finely spaced that there's no way that you can tell practically that it isn't a continuous spectrum of possibilities. You would have to measure energies to literally over 30 decimal places before you could start to notice, oh, it's not holding every specific value, and there's just plain no technology on Earth at all right now that could get even remotely close to that level of accuracy. So this is going to be something that we see in general, and I'll try to tag in on this idea on the way the correspondence principle works for quantum mechanics. Is that you get that you recover classical physics in the limit of large quantum numbers. Okay, so I mentioned that there was one other conundrum from classical physics, and this was the photoelectric effect. This is the basis on which solar cells work. So the idea basically goes like this. I have, historically, it was done with a couple of pieces of metal. Nowadays, you use very precisely engineered silicon compounds because of their very good properties for making it easy to liberate electrons. But you can use metals in principle. And so the idea of the setup goes something like this. I go ahead and I hook some sort of adjustable DC power supply. So just imagine a battery that can somehow change the voltage on. And I turn the knob. And while I'm doing this, I also shine light on one of the plates. We'll call this the emitter. And this plate is the collector. So the electric field is going to run this way, which means if I kick an electron off of here, it wants to go that way. So occasionally light would shine on this, and we kick out an electron, and it will migrate from the emitter over to the collector. And when we do that, we'll measure a current, which we usually call the photocurrent. So the results of this is if I measure the photocurrent as a function of the applied voltage, what we get is that if the light is dim, it looks something like this. And if the light is bright, it looks something like this. But there is an absolute minimum down here. This is what gets called the stopping potential. So this is where the voltage is negative, which means we've reversed the direction of the battery. So what we can understand is the light kicks the electron out, and then the electric force is forcing the electron back on. For a high enough voltage, all of the electrons get forced back to the emitter before they make it over to the collector. Now, what was the classical prediction for all of this? Well, the classical prediction was that there wasn't a stopping potential. And also there are a bunch of predictions, and none of them matched theory, but one was that there was no stopping potential. Another one was that the light, that you would get a photocurrent after you shined the light on the metal for about 2 weeks, was the classical prediction. The actual experimental reality is that it's near instantaneous. So that's a problem. So what we get at, so anyway, we'll just go ahead and hold on to this thought here that the way we can interpret this stopping potential, say that this is telling us what our maximum kinetic energy for our particle is, has to be equal to the charge of, or equal to E times our stopping potential. So the resolution to this is actually due to Albert Einstein, and this is the thing for which he won the Nobel Prize. So Einstein's solution is basically doing Planck backwards. He goes ahead and says light comes in photons. And that the electron ejection is due to the impact by a single photon. And that the photon has to do a certain amount of work to extract the electron from the atom. Or from the atom, we'll say that. This gets called the work function. And I'll go ahead and call it E sub 0, which is not to be confused with rest energy from relativity. Some books call it phi. But anyway, the idea is going to be that the maximum energy, just doing energy conservation, has to be the energy that one photon could offer. So this is the energy of our photon minus the work function. How hard do you have to work to take the electron out of the metal? And this turns out to work out perfectly, matches the experimental data absolutely perfectly. So, for instance, let's go ahead and do a quick example here. Let's say that for some metal, the longest wavelength, which will give us a photocurrent, is 388 nanometers. What's the work function of the metal? So here, what we can say is, okay, our maximum kinetic energy is HF minus the work function. And here we can set this to 0 because we said this is the longest wavelength. The longer the wavelength, the less energetic the photon. So this is a photon that's just barely getting the electron out. So we can go ahead and set the kinetic energy to 0. So in this case, our work function will be equal to HF, and we'll just immediately rewrite that as HC over lambda. HC is 1240 eV nanometers. And our longest wavelength photon is 388 nanometers. This gives us a 3.2 EV work function. And typical energies in atoms are on the order of tenths of EVs to tens of EVs. So this seems like this makes sense. All right, so let's think about what else we might know about the photon. So we can actually use some relativity here to get the photon's mass. If we remember from Einstein's theory of special relativity, we can write that the energy of anything is gamma mc squared. Well, I can rewrite that to say that this is m is E over gamma c squared. Planck says our energy has to be HF over gamma c squared. But the thing is that when you're moving at the speed of light, gamma is equal to infinity. So this means that the mass is equal to HF over infinity times c squared, which is 0. So we get that the photon is massless. And yes, I know this is very sloppy math. You should be doing it as a limiting argument, but the answer stands. However, the photon does have momentum. Remember that we said that one of the invariants was the rest mass of something. So it's mc squared had to equal E squared minus PC squared, where P is the momentum. Here, since the photon is massless, we can set that to 0. We can rearrange to say that PC squared equals E squared. We can take the square root of both sides. PC equals E. We get that the momentum of the photon is E over C. But Planck says that that's HF over C. And so we can rewrite this to say that the momentum of our photon is H over lambda. So the shorter the wavelength, the more energetic the particle and the higher its momentum. Well, that's an interesting prediction. So let's loop back to looking at X-rays and how X-rays scatter. So this is an observation due to an American physicist by the name of Compton, so it gets called the Compton effect. So this is just an experimental observation. I won't go into all the details of the calculation, but I just want to show that this checks out. So we go ahead and have some incident photon. And these photons have to be really energetic, so we're going to be in the X-ray here. At this point, you can just have an electron just hanging out in an atom minding its own business, but that electron is going to get whacked so hard by this, it's going to totally forget that it was ever bound to anything, and we can ignore any binding energies of any of the electrons. So for our purposes, we can just say we have a hapless, poor little electron that's just sitting here. Since we can treat the light as a particle, we can go ahead and do two-dimensional momentum conservation. So the electron scatters off this way, and the photon scatters off this way. And it will be at a different wavelength because it lost some of the energy to the electron. And how much depends on the details of the momentum conservation, so that depends on the scattering angle. So it turns out that the wavelength of the detected light will depend on the scattering angle. These measurements were done, and it checks out. So this particle model of light seems to be working very well. So you might want to ask yourself again, is the wave model wrong? And the answer is no. It works very well in low photon energy situations. So as we think about our wave-particle duality, we'll go ahead and go from long wavelengths here, like the radio on one end, to gamma rays, which are even shorter wavelength than X-rays over here. Over here, the energy of a photon is going to be on the order of 10 to the negative 8 eV. Over here, it's going to be something like 500,000 eV. So here, to detect literally anything, you're going to need to see many photons. And this is where, in an earlier video, I was talking about, we see the wave property by saying the photons are effectively raining in sheets. So the wave property here will dominate. Over here, you only need to see one photon to see something with an energy of 500,000 eV. So over here, the particle property dominates. But this isn't an either-or situation, it's both and. All light has both a particle property, the photon, and a wave property, the electric field, the electric and magnetic fields. And the wave property simply dictates the probability of where you will see the particle. So it's a continuum, but on the extremes over here, you can just say, I'm thinking of this totally as waves because I need to see millions of photons to even notice anything. Whereas over here, I only need to see one. So I'm really thinking of it more as a particle. But we have done the double slit diffraction experiment for very weak light sources. And we have sensors that can detect a single photon pinging onto the sensor at a time. And so what will happen is after a short time, if you were to look at your sensor, you're just going to see randomly splattered photons. However, as you let this go for a long time, you eventually see that the photons prefer to land in specific areas. which perfectly matches the intensity pattern that we saw for double slit diffraction. So it really is both and. That the wave property dictates the probability of where we'll detect the particle. All right, so in the next video, we're going to flip this around. We're going to be saying, okay, so light, which we were treating as a wave, has particle-like properties. Is it reasonable to say that particles have wave-like properties? So we'll go ahead and catch you over in that video.